My name is Wiebke Hutiri. I'm a PhD candidate at Delft University of Technology in the Netherlands, and I work broadly on responsible design of Edge AI, specifically on detecting and mitigating bias. I've been working a lot with speech technologies, so speaker verification, keyword spotting, speech recognition, and I've been quite interested in speech emotion recognition. Speech is a really interesting data source because it's produced by the human body, and what I really like about speech is that it contains two interesting bits of information. The one is information about our physicality, because it's produced by our lungs, by our throat, by our vocal organs. But it also contains a lot of information about our current environment, so the room that we're in, the background noise, the kind of space that we're in, as well as our history, because the way that we speak is formed by our culture, by where we've grown up in. And so like human speech and the voice really has contains a lot of personal information. Challenge that comes with that is that there isn't a one-size-fits-all. And so I've been really interested in bias, so performance disparities that arise because of demographic attributes, because of your age, because of your gender, because of your accent, your nationality, whether you're sick or not sick, and how that manifests itself in speech technologies, and specifically in the on-device setting. So some example of biases in speech is if you take a step back and to say, well, what kind of information content is there in speech data? Speech has a pitch, speech has like a rate of speech. And so bias that, for example, is associated with pitch is that women have a higher pitched voice than men, children have an even higher pitched voice than women. And so, for example, if we take a simple scenario like activating a wake word, okay Google. The speech science shows that women raise their voices when they greet, whereas men lower their voices when they greet. So where a man might then say, okay, Google, women might say, okay, Google. And so for example, if the features that we extract are pitch dependent, we might end up having systems that are more likely to fail in the very specific applications where we want to use them. So pitch is one. Rate of speech is another. Speech slows as we age typically, so you have elderly people speaking often much slower than younger people. And so a very simple thing is we choose windowing functions when we do feature extraction for speech technologies. And a smaller or bigger window, smaller or larger window size might affect how speech is processed if it's spoken slower or faster. And so looking at bias really is taking a step back and saying, if I look at the end-to-end application, from data collection to ultimately deployment, where might my perspective of the world have, how might that have shaped how I've built the product? And because I've been building with data that comes from humans, and humans are different, how might it work for some and not for others? If you do one thing, I would say look at your training data and evaluation data. If I could say a second thing is it's that bias is not only a data problem. And so effectively, the first step that you should do to deal with bias is to test it after you've developed a model. It's not the only thing, but it's the first thing. And so testing for bias involves really three things. The first thing that it involves is having an evaluation data set that enables you to test for bias. So it needs to be sufficiently representative of your entire potential user population. The second is that you need to choose metrics that allow you to see if performance is equivalent across different groups of people that you want to investigate. And the third thing that you need to do is to decide who might the model work differently for and on what basis. And then making a very well-informed comparison of model performance for different groups. I find the tinyML space really interesting in comparison to the bigML space because a lot of things so we found in research that we've done that certain aspects of bias don't exhibit themselves in the large space, in the cloud space. Coming back to the voice space and the way that we do feature processing for voice ML. we typically do a fast Fourier transform, and then create a feature representation called MEL spectrograms. And so the MEL scale is transforms the voice features in a way that it gives more granularity to low-pitched voices than to high-pitched voices. And so that very specific thing in large models on the cloud actually seems not to have mattered so much. But the moment you take, for example, a convolutional neural network that has been trained with 16 kilohertz sample rate, and you now have a lower sample rate, let's say 8 kilohertz, which helps you save battery, so lower sample rate is better for the on-device setting. You also reduce the model size, so you drop, choose a smaller architecture. Then suddenly that MEL transformation actually starts mattering, and you start seeing performance disparities between males and females much more than what you would have seen in the cloud. So my personal view is that even in settings where we wouldn't have seen bias in the cloud, the moment we really adapt models to the resource and hardware constrained on-device setting, we have to go back and see if we could have introduced bias.